Hey everyone, welcome to this explainer. Today we're taking the Ultimate C Handbook and turning it into your absolute foundational guide for low-level coding. Whether you're here to just brush up on some rusty skills, or you really want to finally grasp how computers execute commands under the hood, you are exactly where you need to be. We're going to break down the core mechanics of C programming step by step.
All right, so let's just tackle the elephant in the room right away. Why on earth are we starting our coding journey with the language created by Dennis Ritchie at AT&T's Bell Labs way back in 1972? I mean, half a century in tech years is basically the Stone Age, right? Why not learn something newer? Well, it's a totally fair question, but the answer is exactly why C remains one of the absolute most powerful tools you can have in your tool belt today.
Here's the deal. C literally runs our modern world. It's what we call a low-level, compiled language, which basically means it gives you incredibly fine-grained control over a computer's hardware and memory. And because it's just so remarkably efficient, major parts of the operating systems you use every single day, like Windows and Linux, they're written in C. It's the language driving embedded systems, so it's inside your microwave, your digital camera, your printer. It's even heavily used in game development, where low latency is just absolutely critical, and the machine has to react instantly to user input. So, learning C, it doesn't just teach you how to code, it actually teaches you how a computer thinks.
To keep us on track today, we're going to follow a really clear syllabus. We'll cover 4 main areas. First, speaking the computer's language. Second, the building blocks of C. Third, the anatomy of a C program. And finally, instructions and math in C.
Let's dive right into Section 1, Speaking the Computer's Language.
At its very core, computer programming is just a medium of communication. Honestly, just like you might use English or Hindi to share a thought with a friend, programming is just how we deliver exact, structured instructions to a machine. Computers simply execute directions, and C provides the vocabulary and the grammar we need to write them.
And getting started with this language is surprisingly easy. You really just need 2 basic tools. First, a text editor to write your code, something like VS Code. And second, a compiler, like MinGW. Setting this up is literally as easy as downloading a video game. You just write your instructions in the text editor, and then the compiler steps in to act as your translator, magically turning your human-readable C code into the binary machine code that your processor can actually execute.
All right, moving right along to Section 2, the building blocks of C. To make sense of data, C relies on variables and constants, and I absolutely love the kitchen metaphor used in the handbook for this. Think of variables as the physical containers, like the jars in your kitchen. A jar might hold rice today and dal tomorrow, right? Its contents can change. In code, a variable stores a value that might change as the program is running. On the flip side, we have constants. These are the specific ingredients themselves, like the number 1, the decimal 3.14, or the letter A. They are entities whose fundamental values simply never change.
So let's see how this actually plays out in code. When you write a simple line like int a equals 3, what are you actually doing? Well, you're telling the computer to create an integer variable, a container, and name it a. Then, using that equal sign, you're taking the constant integer value of 3 and putting it right inside that container. It is really that straightforward. Now, along with the variables you create and the constants you use, C has exactly 32 reserved keywords. These are words like int, return, while, and if. The catch here is you cannot use these as names for your variable containers. Why? Because they're reserved words. Their specific meanings are already strictly known to the compiler. They are basically the built-in grammar rules of the C language.
That brings us to Section 3, Anatomy of a C Program.
Every single C program out there, no matter how massive or complex, starts its execution from a core function called main. Inside that structure, you'll use built-in library functions to do the heavy lifting. For instance, printf is a super handy library function that just prints text right onto the user's screen. But pay close attention to the punctuation at the end of that statement. That semicolon is absolutely crucial. In English, we end a sentence with a period. Well, in C, every single instruction must terminate with a semicolon. If you forget it, the compiler gets completely confused and will just throw an error.
Now, as your programs inevitably get longer, you're going to want to leave plain language notes for yourself or for other programmers right there in the code. You do this using comments. You can drop in 2 forward slashes for a quick single-line note, or use a slash and an asterisk for longer multi-line notes. And the brilliant thing about comments? The compiler completely ignores them when it runs the program. They are purely there to help human readers understand the logic.
It's so fascinating how this whole compilation process demystifies the magic of how text becomes actual software. So you write your plain text instructions in a file, let's just call it first.c.
But remember, your computer's hardware cannot read text. It only understands binary electrical signals. So the C compiler steps in. It takes your first.c file, checks it for grammatical errors, and translates it entirely into machine code, spitting out a brand new runnable file called first.exe. And boom, that executable file is the actual software you just created.
All right, let's wrap things up with Section 4, Instructions and Math in C.
Writing a program is honestly exactly like writing a recipe. It's just a sequence of instructions designed to get a specific result. First off, you have type declarations. This is essentially where you gather your ingredients, telling the computer exactly what variables you need. Next, you have arithmetic instructions. This is the mixing and cooking phase, where you perform mathematical operations on those variables. And finally, you have control instructions. These act as the chef's decision-making process, like deciding when to stop stirring or when to turn down the heat.
But here's the kicker. When doing the math part of the recipe, C is incredibly strict about data types. And this is exactly where a lot of beginners get tripped up. The compiler operates on this strict system of type compatibility. If you do math with two integers, the result will always be an integer, period. For example, if you tell C to divide the integer 5 by the integer 2, the answer it gives you is exactly 2, not 2.5. Why? Because an integer container literally cannot hold a decimal, so C just drops that fractional part entirely. If you actually want 2.5, you have to make sure at least one of the numbers is a decimal, or what C calls a float, so something like 5.0 divided by 2. Understanding how values are promoted and demoted like this is absolute key to getting accurate math in your software.
Which brings us to a crucial final thought I want to leave you with today. Consider this math equation, 3 times x minus 8 times y. How exactly does the computer read this? Does it multiply first or subtract first? Well, in C programming, the standard grade school BODMAS rules you learned in math class, they just do not apply. The language actually has its very own strict hierarchy of rules called operator precedence and associativity. So, how exactly does the computer solve this equation? Well, you're going to have to join us in the next explainer to uncover the secret mathematical rules of C. See you then.